Chapter 24. Increasing digestive capacity. Increasing digestive capacity means expanding how much the system can process, transform, and absorb without breakdown or compensation. Capacity is not fixed. It is built from the alignment of neural input, secretory output, structural preparation, and coordinated timing. When these layers are functioning together, the system can handle larger and more complex inputs because each phase receives substrates that match its requirements. When they are not aligned, capacity contracts. The system may still process food, but only within a narrower range, and excess input moves forward without being fully utilized. The first determinant of capacity is neural regulation. The level of parasympathetic activation sets the upper limit for secretion and coordination. When neural input supports digestion, gastric acid production increases, pancreatic enzymes are released in proportion to intake, and bile flow aligns with lipid presence. Blood flow to the gastrointestinal tract rises, supporting both secretion and absorption. This creates the conditions under which capacity can expand. When neural input is constrained, these outputs are reduced, and the system operates below its potential regardless of how much food is consumed. Structural preparation defines how efficiently substrates can be processed. Gastric acid unfolds proteins and alters the physical state of the meal, increasing access for enzymes. Bile organizes lipids into dispersed structures that can be acted on and absorbed. When these preparatory steps are complete, downstream processes operate with less resistance and greater efficiency. This effectively increases capacity because the same enzymatic and transport systems can process a larger amount of substrate when it is properly prepared. Enzymatic activity determines the rate at which macromolecules are reduced into absorbable forms. When enzyme release matches substrate load, breakdown proceeds continuously, and accumulation of partially processed material is minimized. When release is insufficient or poorly timed, substrates exceed the system's ability to process them, and capacity appears limited. Increasing capacity at this level requires aligning enzyme output with the volume and type of incoming material, ensuring that breakdown keeps pace with delivery. Motility and timing govern how long substrates remain within each phase of digestion and how effectively they are mixed with digestive components. Coordinated motility patterns ensure that substrates remain in contact with acid, enzymes, and bile long enough for processing to occur. When timing is aligned, each phase completes its function before progression. When is not, material may move too quickly, reducing processing time, or too slowly, increasing exposure to incomplete substrates and altering the internal environment. Capacity expands when timing allows each phase to operate fully. Lipid digestion plays a stabilizing role in capacity because it provides a sustained flow of substrates that supports continuous energy production and consistent signaling. When fats are properly emulsified and absorbed, they extend the delivery of energy beyond the rapid phases of carbohydrate processing. This reduces variability in substrate availability and allows the system to operate at a higher level without fluctuation. When lipid processing is impaired, this stabilizing input is reduced and capacity becomes more dependent on rapidly changing conditions. Absorption and transport complete the expansion of capacity by determining how efficiently processed substrates are moved into circulation. When transport systems receive substrates in the correct form and at a rate they can handle, uptake proceeds continuously. When substrates arrive in forms that do not match transport requirements or in amounts that exceed capacity, absorption becomes a limiting factor. Improving capacity at this stage depends on the alignment of upstream processes that deliver substrates in a usable form. Increasing digestive capacity, therefore, requires restoring and strengthening the sequence that governs digestion. Neural activation sets the conditions, structural preparation reduces resistance, enzymatic activity completes breakdown, motility maintains timing, and transport delivers substrates into the system. When these elements are aligned, the system expands its ability to process input and convert it into usable output. Capacity is not increased by forcing more input into the system, but by improving how that input is prepared, processed, and absorbed. Gradual system reloading. Gradual system reloading restores digestive capacity by increasing input in a way that matches the system's current processing ability while allowing each phase of the sequence to strengthen. After a period of constrained digestion, the system adapts to lower output. Acid production, enzyme release, bile flow, and motility operate at reduced levels because demand has been low or inconsistent. Introducing a large substrate load into this state overwhelms the sequence immediately. Substrates exceed processing capacity, incomplete material accumulates, and downstream effects reappear. Reloading avoids this by scaling input to the system's present capacity and expanding that capacity over time. The process begins with controlling substrate load per exposure. Smaller, well-defined inputs allow gastric acid to reach effective levels relative to the amount of protein present, enabling full structural modification before progression. This creates substrates that downstream enzymes can access without resistance. As this pattern repeats, acid production adapts upward because the system is repeatedly asked to meet a slightly higher, but still manageable demand. The increase is incremental, and each step reinforces the next. Lipid introduction follows the same principle, but with additional dependence on bile coordination. Moderate amounts of fat stimulate bile release and establish the timing relationship between gastric emptying and intestinal processing. When lipid input matches the system's ability to emulsify and absorb, fats are processed efficiently and provide sustained substrate flow that stabilizes energy delivery. Increasing lipid load gradually allows bile production and release patterns to adapt without creating accumulation of poorly processed fats in the intestine. Enzymatic capacity expands in response to repeated exposure to substrates that have been properly prepared. When proteins are unfolded and lipids are emulsified, enzymes operate efficiently and complete breakdown within the available time window. Repeated successful processing reinforces enzyme release patterns and maintains alignment between substrate load and catalytic activity. Increasing input too quickly disrupts this alignment, forcing enzymes to operate on substrates that exceed their capacity or are not structurally prepared. Motility adapts alongside these changes by maintaining coordinated movement that matches the rate of processing. Smaller, controlled inputs allow mixing and progression to remain synchronized with enzymatic activity. As input increases gradually, motility patterns adjust to handle larger volumes without losing coordination. This preserves contact time between substrates and digestive components, preventing the premature movement of partially processed material. Transport systems complete the reloading process by absorbing substrates that have been fully reduced. When inputs are scaled appropriately, transport occurs continuously without saturation. This reinforces the entire sequence because successful absorption reduces the accumulation of material within the lumen and supports stable delivery of nutrients into circulation. As capacity increases upstream, transport adapts to handle the increased flow. Gradual system reloading therefore rebuilds digestive capacity by aligning input with current function and expanding that function through repeated, successful processing. Each phase is reinforced in sequence. Acid prepares, bile organizes, enzymes complete breakdown, motility maintains timing, and transport delivers substrates into the system. Increasing input only after these steps are operating effectively allows capacity to grow without triggering the same failures that reduced it. Expanding food tolerance. Food tolerance expands when the digestive system regains the ability to fully process a wider range of substrates and deliver them in forms the body can use without triggering compensation. Tolerance is not a property of the food itself. It is a function of capacity. When digestion is aligned, proteins are reduced to amino acids, carbohydrates are converted to simple sugars, and lipids are emulsified and absorbed in a controlled pattern. These forms pass through the intestinal barrier without generating excess immune signaling. When digestion is incomplete, larger fragments and poorly processed substrates remain in the lumen, increasing the likelihood that the system reacts to their presence. Expanding tolerance therefore requires improving how inputs are processed, not simply changing which inputs are consumed. The first step is restoring structural preparation so that substrates entering the intestine match the requirements of enzymes and transport systems. Adequate gastric acid unfolds proteins and reduces the physical resistance of the meal. Coordinated bile release organizes lipids into dispersed structures that can be accessed and absorbed. When these steps are consistent, downstream processes operate with less friction, and a greater proportion of the meal is converted into usable forms. This reduces the amount of material that reaches distal regions in a partially processed state. Timing and pacing determine whether this preparation is maintained as input increases. Smaller, controlled exposures allow the system to process substrates completely before introducing additional load. As capacity improves, the range and quantity of inputs can expand without exceeding processing ability. Each successful exposure reinforces the sequence, allowing the system to handle more complex or previously problematic foods. Increasing input too quickly disrupts this progression, reintroducing incomplete processing and limiting tolerance. Lipid digestion contributes to tolerance by stabilizing the internal environment of the intestine. Properly emulsified and absorbed fats provide a sustained source of substrates and influence how other nutrients are processed. This stabilizing effect reduces variability in substrate delivery and supports consistent signaling across the system. When lipid processing is impaired, this stability is reduced and tolerance becomes more sensitive to changes in input. Microbial activity reflects the state of digestion and influences tolerance indirectly. When substrates are fully processed and absorbed, less material reaches distal regions for fermentation. When digestion is incomplete, increased fermentation alters the internal environment and contributes to variability in how the system responds to food. Improving upstream processing reduces this substrate load and shifts microbial activity toward a pattern that supports stability rather than variability. Immune signaling decreases as processing improves because fewer incomplete fragments reach the intestinal interface. The barrier is exposed to substrates that match transport requirements rather than larger or irregular structures. This reduces the signals that drive reactivity and allows tolerance to expand. The change is not achieved by suppressing the immune response, but by reducing the conditions that provoke it. Expanding food tolerance therefore follows from restoring the digestive sequence and increasing capacity in a controlled manner. Structural preparation, coordinated timing, enzymatic breakdown, and efficient transport convert a broader range of inputs into usable outputs. As this process stabilizes, the system handles more foods without triggering downstream effects, and tolerance reflects the improved function of the digestive system rather than the restriction of inputs.